Welcome back to Integral Calculus. In this video, I want to introduce you to power series representations of functions. That title is probably meaningless to you at the moment, so let me get my head out of the way and we will dive right in. A power series is any function which can be written in the form f of x is the sum, k goes from 0 to infinity, of ak x to the k. And if you start writing out the first couple of terms of a power series, we can see that approximately this is going to be, well, when k is 0, we'll have a sub 0 times x to the 0, but x to the 0 is just 1. We don't have to bother writing that down. And then we'll have a1 times x to the first power, and a2 times x to the second power, a3 times x to the third power, and so on. So a more useful but technically not precise definition might be that a power series is an infinite degree polynomial. One of the interesting things about a power series is that when we can write the power series is the function is the power series. And for a number of functions that we are very familiar with, there is a convenient way of representing that function as a power series. The first one that most textbooks lead off with is to remind you of the geometric series. The geometric series is the sum. Generally, n goes from 0 to infinity of a times r to the n. And we know that the geometric series converges and becomes a over 1 minus r when r in absolute value is less than 1. And so we might decide to write a geometric power series. We'll generally switch from n to k at this point. So k goes from 0 to infinity. And we'll just replace the r with x. So we have some constant a times x to the k. And this will converge and will give us that a over 1 minus x whenever the absolute value of x is less than 1. And so that is our basis. If we have a particular rational expression, that might be something like 3 over 1 plus x squared. Well, comparing to the geometric series, instead of having an a on the top, we have a 3. So I guess our a is 3. And then instead of having a minus r, we have plus x squared. So minus r is plus x squared, which means that r itself is minus x squared. And that looks a little bit goofy, but that is in fact a power series. We might choose to rewrite this, clean things up a little bit. Some k goes from 0 to infinity of 3 times minus 1 to the k times x to the 2k, just using some properties of exponents to get rid of those parentheses. And sure, it looks a little bit weird to have x to the 2k instead of x to the k, but that is still perfectly valid. If we expand this out, it is still a polynomial. We're just skipping a bunch of terms. Right? When k is equal to 0, we will have 3 minus 1 to the 0 is 0. X to the 2 times 0 is 0. We don't have to write any of those out. When k is 1, we have 3 times minus 1, which is minus 3, times x to the 2 times 1, so that's x squared. And then we will have plus 3x to the 4th, minus 3x to the 6th, and so on. So it is a polynomial. It only has the even terms, but it is still a polynomial, and it still satisfies that rule of power series. The place where the entire idea of power series really shines, though, is in Taylor or Maclaurin series. We've seen that we can approximate a polynomial or a function as the polynomial f of 0 plus f prime of 0 times x plus the second derivative evaluated at 0 divided by 2 factorial times x squared, and so on. If we can take all of those derivatives and we can evaluate them nicely, this just taking the limit as the polynomial grows will give us the power series. So f of x, again, taking the limit, turning it into a power series, this is no longer an approximation. This is equal the sum. K goes from 0 to infinity of the kth derivative evaluated at 0 divided by k factorial times x to the k. Notation here is a little bit weird in the first couple of aspects because we don't often use that k exponent, and we especially don't use it for the k equals 0 case. So the convention here that we need is that the 0th derivative of a function is the function itself. So when we plug in the 0th derivative, we get f of 0. When we plug in the first derivative, we get f prime of 0 divided by 1 factorial. Then the second derivative would be f double prime, again evaluated at 0, divided by 2 factorial in this case. And that is the Maclaurin series. Remember, it's called a Maclaurin series if it's centered at 0. It's called a Taylor series if it's centered anywhere else. I don't know why we have to have multiple names for it either, but multiple names we do have, and so we just work with it. All right, so evaluating at some center point C instead of K, or instead of x equals 0 is fine. But then instead of having x as our base for the polynomial, it will be x minus c instead. And that is the Taylor series. I don't remember if I mentioned, sorry about that, I pushed the wrong button. That's the button I wanted. I don't remember if I mentioned this in the video on Maclaurin polynomials or not, but in mathematics, we care about precision in naming, and so we have this separate name for Maclaurin series and Taylor series. In physics and engineering, most instructors are too lazy to look up the difference, and will just generalize and always call it a Taylor series. Whether it is a polynomial approximation or an infinite series, whether it is centered at 0 or centered somewhere else, it makes mathematicians want to tear their hair out. I am really glad that I'm wearing my math teacher hat today and not my physics teacher hat, because when I'm wearing my physics teacher hat, I get frustrated with myself. we looked, when we were talking about Maclaurin polynomials, at the function f of x equals e to the x. It's a very simple function to work with because no matter how many derivatives of e to the x you take, you still get e to the x. That makes the exponential incredibly important in a number of applications. The further you go on in mathematics or any of the applied mathematical sciences, the more you come to rely on e to the x. But then also, whenever you evaluate e to the x at x equals 0, you always get out 1. So we can write the Maclaurin series for the exponential function. E to the x is the sum, k goes from 0 to infinity, of, well, the derivative 1 times x to the k divided by k factorial. That is a worthwhile formula to know offhand. Especially if you are continuing onward in your study of mathematics, it will come up again. A little bit trickier is the function f of x equals sine of x. Because in this function, we end up with a bit of a rotation. Starting with the function sine of x, the first derivative is cosine, the second derivative would be negative sine, the third derivative would be negative cosine, the fourth derivative would be sine again, and that takes us back to the beginning. If we're trying to write the Maclaurin series, that means we're centered at x equals 0. We want to evaluate all of these things when x is equal to 0. And I'm not going to even bother writing the fourth one out because it's cycling back to the beginning. But sine of 0 is 0, and the opposite of sine of 0 is still 0. Cosine of 0 is at least a little bit interesting. Cosine of 0 is 1, so the opposite of cosine of 0 would be negative 1. And we end up with this repeating pattern of 0, 1, 0, negative 1. This is one of the places where I think that writing out the polynomial approximation first makes life a lot easier because you can start to see what is happening. We're going to end up with 0. And I'm even going to write it out with the explicit divided by 0 factorial. And then we have f prime of 0, which is 1 divided by 1 factorial times x to the first. And then we have 0 divided by 2 factorial times x squared. We have negative 1 over 3 factorial times x cubed. We have 0 divided by 4 factorial times x to the fourth. We have 1 over 5 factorial times x to the fifth. I think that writing that out makes it a lot more obvious that for the even exponents, we get 0. So we want just odd values. This is where it really comes in handy to remember that if k is the sequence of all numbers, then 2k would be the sequence of just even numbers. Right? Plugging in k equals 0, 1, 2, 3, and so on, you would get 0, 2, 4, 6, 8. Plugging in to 2k plus 1 will give you the odd numbers. K equals 0 spits out 1, k equals 1 spits out 3, and so on. So once we use that substitution, we can realize that this first non-zero term, x to the first, is the k equals 0 term. Negative 1 over 3 factorial times x cubed will be the k equals 1 term, and 1 over 5 factorial times x to the fifth will be the k equals 2 term. Why is that useful? Well, that gives us something to do about the negatives. Because when this k is odd, we have a negative coefficient. And when this k is even, we have positive coefficients. That's something that's really easy to work with. So we want our sum. K is definitely going to start at 0 and go to infinity. Instead of x to the k, we're going to use x to the 2k plus 1 power. And then our factorial, again, instead of k, has to be 2k plus 1 factorial. That will give us our 1, 3, 5, 7, and so on. But then we also need to alternate between positive and negative numbers. And the simple construction, negative 1 to the k. If k is even, negative 1 to the k is equal to 1. If k is odd, negative 1 to the k is equal to negative 1. And so that will give us exactly our pattern. If you're not quite sure where all of that came from, take a minute here to pause the video and write out the first couple of terms of this power series and just verify for yourself that you're getting the same polynomial that we started playing around with. Right. I think that that's the basic idea down. I don't think there's too much more I can say on the topic. So let's wrap up with one for you to try. F of x equals natural log of x comes with its own little bit of baggage. Very specifically because the natural log is not defined when x is equal to 0. So this is one of the places where the Maclaurin series just doesn't work. Well, if 0 doesn't work, we have to choose something else. The easiest something else I know of is x equals 1, and that's what I would like you to look at. Using the tools that we've developed of Taylor and Maclaurin polynomials and the power series we've been looking at in this video, I would like you to write the power series representation of f of x equals the natural log of x centered at equals 1. Take a couple of minutes, see where you can get to with that, and I'll see you in the next video.